Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 12, 2025, which was about 5 days ago. The big result is a unified optimization framework that ties together steepest descent, Quasi-Newton, and adaptive methods, and it yields new optimizers that are competitive and sometimes outperform the state-of-the-art. The paper is titled Preconditioned Norms, a unified framework for steepest descent, Quasi-Newton, and adaptive methods, and the implications for model training are quite significant. In short, the authors formalize matrix-level affine and scale invariance, and introduce MuAdam and MuAdam-SANIA that stay robust under rescaling, and show strong results across language and vision tasks. Also, the authors shared a GitHub repo that packages the paper's ideas into code. You will find a first-order optimization library with MuAdam and quasi-descent implementations, runnable notebooks for comparisons and visuals, scripts to reproduce experiments, a small bool Q data stub, utilities to extract weights and biases and LLM results, and a clear requirements file. Alright, the previous segment covered the code release and practical setup. Theorem 1 presents the linear minimization oracle in the preconditioned norm framework, which operates in a transformed gradient space. For two-sided preconditioning, the gradient is mapped by inverse transposes on the left and right, the base oracle acts, and the result is mapped back by the inverses. For element-wise scaling, the oracle works after rescaling entries, and then reverses that scaling. Okay, the previous segment laid out the linear minimization oracle mechanics. Table 1 organizes popular optimizers within the unified template, mapping each method to left and right preconditioners, LT and RT, any diagonal scaling DT, and the base norm. The dashes indicate unused components, and EMA flags exponential moving averages. The hybrid block lists MuAdam and MuAdam-SANIA, which pair spectral geometry with Adam-style diagonal moments, so the unification spans norm-based, quasi-Newton, adaptive, and hybrids. Well, Table 1 grouped methods under one template, and Algorithm 1 now spells out MuAdam and MuAdam-SANIA. The algorithm maintains Adam's style first and second moments, then applies an element-wise preconditioning that divides the bias-corrected gradient by the second moment to the power page. A spectral linear minimization oracle follows, computed with the Newton-Schultz routine, which injects Muon spectral geometry. A second diagonal scaling comes next, and the step updates the weights using this twice preconditioned search direction. So Algorithm 1 detailed the hybrid update, and Figure 1 presents the scale invariance test on mushrooms. The left panel shows training loss on a log scale, where Adam W and Muon drift upward on scaled inputs, while Adam-SANIA and MuAdam-SANIA trace overlapping curves. The right panel reports test accuracy, which stays high and aligned for the scale invariant methods but drops for the non-invariant ones. The spectral plus diagonal hybrid matches or edges the diagonal baseline. Alright, Figure 2 shows LLM fine-tuning results on QN27B across bool Q, Hella Swag, and Arc Challenge. The left group indicates MuAdam leads with about 72%, topping Adam W and Muon. The middle group again favors MuAdam near 74%, which signals consistent gains on common sense tasks. The right group flips the ranking, with Muon slightly ahead and MuAdam closer to 75%. Error bars display variation across 3 seeds. 2 takeaways stand out. Preconditioned norms give a single lens that explains steepest descent, quasi-Newton, and adaptive methods, and the framework provides crisp conditions for affine and scale invariance at the matrix level. The broader implication is a principled design space that yields robust, high-performing optimizers, like MuAdam and MuAdam-SANIA. Thanks for listening. I am Alex, signing off.